Good morning, good afternoon, and good evening. Thank you for your interest in fog computing, and thank you for joining us. I'm Lynn Canavan, the Executive Director of the Open Fog Consortium, and it's my pleasure to welcome you to the first webinar in our new series, Out of the Fog. This on-demand webinar series is designed to give short bursts of education on various elements of fog computing. The Open Fog Consortium is a public-private ecosystem formed to accelerate the adoption of fog computing in order to solve the bandwidth, latency, and communication challenges associated with IoT and other advanced digital scenarios. OpenFog was formed by ARM, Cisco, Dell, Intel, Microsoft, and Princeton University in November 2015. Today we have members located throughout North America, Europe, and Asia. And now it's my pleasure to introduce today our speaker, who is Aapo Markkanen, who is a principal analyst at Machina Research, where he studies various market and technology issues that will pave the way for and shape up tomorrow's connected enterprise. Aapo has a particular interest in low-power communication technologies, the evolution of IoT security, and fog edge computing and the associated IoT gateways. Before joining Machina Research, he worked as a principal analyst at ABI Research, where he led various research activities related to M2M, the Internet of Things, and big data. He holds a Bachelor's of Science and Master's of Science degrees in Management Studies from the University of Tampere in Finland. And we're also delighted to team with Machina Research on today's webinar. Machina Research is the world's leading provider of market intelligence and strategic insight in the rapidly emerging machine-to-machine, Internet of Things, and big data opportunities. And they were one of the earliest research organizations to cover fog computing. So now it's my pleasure to welcome Aapo. Thank you.
Yes, thank you for the introduction, Lynn, and welcome to the webinar, everyone. Thank you for your time. To start off, I wanted to bring up this high-level diagram of an IoT system and its different elements. This is meant to illustrate the different points where IoT data can be stored and processed. So first, there is the end node that actually generates the data, and this is what represents the so-called local level. It's worth remembering that much of the data that is ever generated, for example, by sensors, is usually discarded already at the source without further processing. So only the readings that are flagged up as being relevant, either based on time or selected sensing thresholds, can then get sent onto the next level. And this next step is what we call the aggregation level, which collects data from various end nodes and aggregates them accordingly. On one hand, this consists of devices such as routers, access points, and concentrators. I have taken the liberty to call these collectively gateways. And on the other hand, on this level, we can also find somewhat more capable devices like data historians and local servers. In this exercise, I refer to them as the site backend. From the site backend, the data travels onto the enterprise backend, which covers on-premises equipment and private clouds, mostly. And finally, you've got the remote data centers that accumulate data from all of the steps before them. As a category, I've termed this third level of the enterprise backend data centers as the cloud level. Capabilities that these different forms of IoT infrastructure have for storing and processing data increased by each step. And the same goes naturally for the number of data sources that they deal with. So in intelligence systems, the local and aggregation levels constitute edge intelligence, while the cloud level represents centralized intelligence. Models that substantially apply both forms of intelligence can be best described as distributed intelligence in this context. So this is the kind of conceptual backdrop that we have for today's topic. And then moving on, let's talk a little bit about what actually makes edge intelligence important in IoT, and thereby why there is such a strong case also for fog computing. In these early days of IoT, products and services tend to be built largely on centralized intelligence. The main goal often is simply to get the end devices connected in the first place and then handle the data and initiate actions predominantly from the cloud level. As an architecture choice, centralized intelligence involves less complexity than more edge-centric models, but getting it right can already be extremely daunting. So it's quite understandable that this is where the most enterprises that are working on IoT are actually focusing on. There are some exceptions, especially amongst the companies that have background in industrial automation. In those cases, the intelligence has pretty much out of necessity and by default always resided on the local aggregation levels. And for these types of players, IoT is basically just a more evolved way of automating and quantifying their existing processes. What is starting to happen, however, is that as computing and storage become more viable in smaller devices and more constrained environments, there is an increasingly strong case for distributing more intelligence from the cloud to the edge. I've summarized the benefits of doing this in here. First, it helps the enterprise to do more advanced things with all the data. On one hand, they can use more sophisticated filtering on data streams and thus produce better insights once they analyze the data on the cloud level or in the enterprise backend. And on the other hand, it becomes also possible to run more complex analytical models already at the edge and automate actions in real time or near real time. The second deals also the security and compliance aspects. Handling more data at the edge and transmitting only what's really needed to the cloud can reduce the so-called attack surface that exposes the system to potential intrusions. More intelligent edge devices can also be made more technically robust, for example, in terms of encryption of the data. And then besides that, the actual security, there's also a slightly different dimension in compliance with, for example, privacy regulations. If you take, for instance, CCTV systems, then in many jurisdictions, there are privacy laws stipulating that the recorded video content cannot be stored outside the premises. In such circumstances, often the only way of running meaningful video analytics is to analyze the content already at the edge. And then third, there's the benefit of improving the reliability of the entire system. Edge intelligence can remove single points of failure from the network and help ensuring that the application can still function even if there are technical problems in the enterprise backend or in the data center. So that was the case for a more intelligent edge in general. The next, let's discuss where fog computing actually fits in here. You see, the edge computing as a concept as such is nothing new or novel. As I mentioned earlier, it has been the norm in industrial systems basically ever since they have existed. However, the thing is that in its traditional form, edge computing is a very siloed concept. Processing and storage is done by individual devices, and the data sources that these devices handle are also pretty limited and static. As a rather meta example, as they say in the internet, I have here a hypothetical group of smart grain silos. The sensors inside of them measure anything from temperature to humidity to grain levels, and the readings are aggregated individually for each silo. The people who own the silos check the status one by one on the spot, or if they have got them connected to a local area network, then they can do the monitoring from the site's PC, for example. So this is how things work in the traditional edge computing before the fog comes into play. And then next up, let's discuss how things in the this kind of same hypothetical example look under the fog paradigm. The big difference here is that if you compare with the traditional edge computing, the difference really is that these previously closed silos open up, figuratively in this case. You can see how the computing devices inside of the silos are interworking with each other, sharing data and distributing storage and processing workloads with each other. And then at the same time, they're also connected to other gateways on the site. There's one on the ground level, aggregating data from sensors across the farm and from the fleet of harvesters and other machinery. Then there's another gateway on the top of the silo structure, which is connected with the farm's own microgenerations plant, whether it is solar panels and wind turbines. as well as with the fleet of drones that I use to, for instance, to optimize the irrigation system that covers the fields down there. This gateway on the top also serves as the backhaul link to the cloud. And the cloud platform then is used to provide an enterprise-level view of the farm's operation, and it's also used, for example, to do machine learning in order to enhance analytics that are then applied on the site. I think it's good to highlight how important these various gateway devices are for deployments like this. So gateways play a significant role in enabling connectivity in challenging network environments. So that is when the nodes are dispersed across great distances and connected by using multiple protocols. That's normally the case if you purchase IoT devices from various suppliers. Then it can be quite a big technical headache to get all these protocols interworking with each other. And at the same time, then gateways can be increasingly used to store and process the data that they aggregate. Gateways that serve both of these purposes, so communications and computing, are what we call intelligent gateways. And they can be seen as the single most instrumental building block in fog networks. What we have here is a kind of assessment of some of the end markets and applications where fog computing and intelligent gateways are likely to have the greatest impact. The vertical axis of this chart aims to differentiate between these opportunities in terms of the focus of data analytics. If you take, for instance, usage-based insurance or water metering, then these are what we consider very cloud-centric applications for the purpose of analytics. With them, most of the intelligence resides on the cloud level by default. Then for comparison, video surveillance and operating an aircraft are examples of the activities where the most important uses of analytics are done more or less locally in a tightly integrated device environment. And then there are applications in this kind of middle layer where the focus of data analytics is strongly on the aggregation level. This covers areas where data becomes more valuable when it's aggregated from a variety of sources, but at the same time analyzed close to the source rather than in the cloud. So you've got smart electricity grids, venue management, or upstream oil and gas production as some of the examples there. And then to capture the other dimension that's important to gateways, we also have horizontal axis here. This deals with the complexity of communication protocols. The point being that higher complex protocol environments require more capable gateway devices. The markets that fall under that orange sweet spot, the sweet spot area there, can be considered the ones where fog computing and intelligent gateways are likely to have the greatest impact based on our research. To generalize a little, most of these are what could be regarded as segments of the industrial Internet of Things. Yeah, then to wrap it all up, here are the 5 key takeaways from this introduction. First, I want to stress that fog and edge computing are not the same thing. There's a major conceptual difference in the sense that the fog is about pooling data and resources without any metaphorical silos. Second, fog computing does not mean that the systems using it will become reliant on the fog and edge intelligence exclusively. The cloud is also an important part of this new paradigm. The point is that the developers that build IoT applications can deploy certain application elements in the cloud, some others on the aggregation level, and some others finally locally within the node itself. And third, I'd like to highlight the role of intelligent gateways as the key enabler for fog architectures. Innovation of these types of devices will be critical for the fog paradigm, most likely. The fourth, this intelligent gateways and fog computing as a concept stand to make the biggest impact in the industrial IoT. If you take that earlier list of the benefits benefits of fog computing that I had there in the beginning, then those by and large apply especially to the complex and mission-critical application environments that you can then find in the industrial space. Finally, I want to make a point that most likely will be covered very well indeed in the upcoming parts of this webinar series. The creation of a true fog network will require multi-vendor interoperability. Without this, there simply won't be enough available data resources to be pulled, and we can't get much beyond the traditional edge computing paradigm. For this reason, as an analyst, I think it's very important that we have something like Open Fog Consortium to drive the collaboration effort that's needed for this interoperability to become a reality. The fog as such holds a lot of promise, and at Machina Research, we believe it's a very transformative force in the Internet of Things going forward. But for that to happen, really, we do need the interoperability across different suppliers. So that's really this challenge that needs to be addressed.
Thank you, Apo, for that very excellent introduction to fog computing. This concludes today's recording. For more information, please contact Machina Research or visit our website at openfogconsortium.org. Thank you.